Every single minute, creators upload 500 hours of video to YouTube. On the other end of the connection, the platform serves 1 billion hours of watch time to billions of concurrent users every day. Operating at this volume requires the platform to coordinate 3 distinct infrastructure roles. It must function as an exabyte-scale storage drive, an ultra-low latency streaming network, and a real-time search engine simultaneously. The traffic pattern is entirely asymmetric. For every 1 write operation to the system, there are roughly 100 read requests pulling data out. To survive this massive imbalance, YouTube completely decouples the heavy, static, raw video files from the lightweight, highly volatile metadata that describes them. If you try to upload a 4 GB video over a single HTTP request, a minor network drop on the user's end means the entire file fails. The connection drops and the server throws out the data. Instead, the platform uses resumable chunked uploads. The large video is fractured into tiny, discrete data blocks. As these chunks hit the ingestion server, they trigger a lightweight completion event, firing a pulse sequence into a message queue known as Apache Kafka. The moment that completion event hits Kafka, the server immediately severs the user's connection. The upload appears finished on their screen, while the actual file processing continues asynchronously in the background. Separating the receipt of the file from the processing of the file ensures that slow client uploads cannot tie up server connections and crash the ingestion pipeline. The raw MP4 file a creator uploads is never actually served to a viewer. Instead, it triggers a directed acyclic graph, or DAG, a cascading pipeline routing the file across parallel worker nodes. These FFmpeg worker clusters simultaneously transcode the raw video into 6 different resolutions. Each resolution is further encoded into 3 distinct codecs, H.264, VP9, and AV1. The final destination for this massive matrix of transcoded video blobs is Google's Colossus file system, a distributed deep storage network. The system absorbs an intense computational cost up front to ensure that every possible version of a video is ready for frictionless delivery downstream. While the static video files sit in Colossus, the volatile metadata, the titles, tags, and user IDs, requires an entirely different architecture. Relational data typically lives in a MySQL database, but a single physical disk has strict input-output limits. During a massive traffic spike, thousands of concurrent client connections swarm a single database instance, causing it to crack under the load. Engineers call this the thundering herd problem. Historically, the only way to prevent this was to force application developers to write complex manual sharding logic directly into their code to divide the database queries. YouTube bypassed this by building Vitess, a custom middleware shield that sits directly in front of the primary database to catch incoming queries. Vitess uses a technique called connection pooling. It takes thousands of simultaneous client requests and multiplexes them down into a tiny handful of actual MySQL connections. Behind the scenes, it evenly sorts and distributes those queries across dozens of smaller parallel databases. Vitess isolates the state bottleneck. It gives infrastructure engineers the power to scale relational data horizontally without exposing that sharding complexity to the application developers. When a user clicks play, their read request bypasses the deep storage Colossus system entirely and routes to a Google Media CDN edge node located as close to them as possible. The delivery relies on a protocol called adaptive bitrate streaming. YouTube doesn't send a continuous video file. It sends a manifest file, mapping the video into discrete 2 to 10 second segments. The client player continuously pulls differently sized blocks based on the available bandwidth. The logic lives entirely on the user's device. The client continuously measures its network speed. If the connection suddenly degrades, the player instantly stops pulling large blocks and selects a low-resolution block for the next segment, keeping the stream alive without pausing. This delivery happens over QUIC, which is HTTP/3 operating over the UDP transport layer. QUIC avoids TCP's head-of-line blocking problem. Because the streams are independent, a single dropped packet on a lossy cellular network won't freeze the rest of the video data waiting behind it. Pushing the complex buffering logic down to the client device allows YouTube's edge servers to simply sit back and blindly serve static chunks at maximum velocity. We can test this architecture against its most extreme edge case, a viral video triggering a sudden, localized 100x traffic spike. If YouTube attempted to update a single MySQL row directly for every new view, the simultaneous write requests would cause a catastrophic write lock across the system. The first layer of defense routes these high-velocity view events into Redis. This is a temporary in-memory cache that instantly records an approximate view count. For the second layer, the actual durable view events trickle into an Apache Kafka log, gathering the raw data securely without overwhelming the final destination. Finally, a batch processing job periodically wakes up, counts the exact Kafka logs, and reconciles them with the permanent MySQL database. The ingestion DAG processes writes. Vitess manages the core metadata, and the CDN delivers reads via adaptive bitrate streaming. Maintaining stability at this scale requires decoupled pipelines that isolate volatile state changes from the delivery of massive static video files.